last talk will be on a wireless application overlay for ubiquitous mobile multimedia sensing and interaction. The speakers are Hanno and Ruth from University from Germany.
Can anyone hear me? So welcome to my talk. It's about a very long title. I will explain what it means. I'm Hanno. The rest of the co-authors are listed there. So let's start. As a motivation, mobile users, just like us, are ubiquitously surrounded by wireless devices. And that means smartphones, access points, IoT devices, whatever you have, right? So there's a wireless connection establishment or wireless capabilities, more or less everything. So if you think about this in a horizontal space where you are and where the other devices are, there's typically some devices around you that you can communicate with. And you do get from that a physical wireless context, meaning that within the range of your transmission, there are people you can talk to. And that creates a multimedia context that is quite unique and dynamic to your position, to your time, to what you want to do. The content and the applications that other devices run on their smartphones or systems, they give you that content which you can exploit or could exploit. And the nice thing about this is many applications coexist in that space at the same time and in the same place, and it's completely autonomous. So you don't need any discovery service for that, or at least you wouldn't need if what we propose comes through. And it's autonomous from internet access or something like that. So you can have that while being me on the streets of Singapore without an internet uplink, you can do that. And from that, you can think of a lot of applications which are more in the multimedia domain or in the, I don't know, use case domain and not so much in my networking domain. But you can think of mobile gaming. Within the location that you are in, you could share media, just like the previous talk proposed, but locally. You could sense stuff, for example. You could sense the photos and the impressions that others create of this content. You could do augmented reality, and so on and so forth. So why is this in any case relevant? Why do we propose something if we all have an uplink and stuff like that? So if you look at current multimedia approaches, all they want from you is one type of information that they isolate from the current context and then upload them to the internet, to one service that provides the service to you, that gives you back the data you're interested in. And that is very application specific, and that it means you have one service for one application. And you have, for example, I'll come to the examples later, you have databases, 3D models for localization, the gaming infrastructure. And let's look at some examples. If you think about a simple walkie-talkie app where you want to broadcast an audio stream to the participants in your immediate surroundings, like the kids' toys, right? You can use it for emergency and info, so serious use cases. You would need to record the audio, send it up to through your internet connection up to a service in the internet where there's a database, and the database takes care of finding the participants around you that would be interested, that are in your range. And then it sends down the content to the participants in your range. So it's up and it's down to everything that I mentioned, although the people you want to reach are in your immediate vicinity. Or another game example would be the Google or Niantic English game, where you have a location-based gaming in which you fight with other players for landmarks in the real world. Of course, those real-world landmarks are virtually represented by Google. I will show some images of that later. So what it does is, it takes your immediate surrounding, it takes the real world that you walk in, that you interact with gamers and landmarks in, and it does a full virtual representation, although you are in that surrounding at the very moment. So that comes to the problem statement we want to solve. If you do have a context, a multimedia context, currently all approaches completely detach from that and upload very specific pieces of information up to internet services, which prevents you from sensing what's around you, what type of media is around you, who's around you, and so on and so forth. And again, from my point of view, more from the networking side, that's because wireless networks restrict who you talk to and when you can talk to them. For example, now, here, we're probably all logged into the wireless SMU network, but that means we can only talk to those guys. If I move out of the network, I can't talk to you anymore because I'm not in the network. So that creates, for any type of wireless network you look at, a vertical hierarchy, meaning you need to go to your 3G, 4G access point, or your wireless access point, or a gateway in smart object deployments to simply be able to talk to guys in the network. You can't talk to anyone outside of it, which restricts it, right? So the state of the art, we talked about the commercial multimedia approaches, internet-bound and application-specific, which very much narrows down the context you're able to exploit. And if you look at networking techniques that would allow you this horizontal, this local communication, there's standards that take care of that. It's, for example, Wi-Fi Direct and Bluetooth. But what they do is they create one specific network between the participants that make up the network. And again, you can't talk to anyone else. So in every context, you would need to cycle through all the networks or establish a network with all the participants, which is very much overhead. In terms of the academia side, multimedia approaches typically assume that there is a networking infrastructure already available. One example is a very, very, very nice game from MMSys 2012, I think, where you can make a sword fight between phones, mobile phones, without any sort of infrastructure between the phones, but you need to relay the information over a wireless network in between. So it's not completely detached from network requirements. And very close to what we do is the concept of heterogeneous networking, where you think of 3G or 4G appliances providing content to local networks, which then take up the load of the carrier networks. But then again, everyone needs to be in the same local networks to be able to communicate, to be able to create multimedia approaches between the local participants. So what we try to do, or what we propose, is a wireless application overlay, meaning for your locality, for your immediate surroundings, wherever you are and whenever you do that, we want to give you unrestricted access to all the context that you can experience over wireless. Meaning you can find content, you can find applications, you can find people, you can share media, and so on and so forth. And that should only be determined by what the local device is capable of seeing in terms of wireless communication. And then, of course, we want to expose that context to multimedia applications, which may make use of that. So as an overview, this is a very crude graphical representation of the system. Painting is not my strong suit. We do need access to the wireless medium, right? And what we need especially is a network-less communication layer. Otherwise, we would still have the restrictions of wireless networks. And we try to do this in an abstraction layer to hide all the networking characteristics from the applications. Currently, we cater to 802.11 and 802.15.4. 802.11 is, of course, in every smartphone, and this is the prevalent wireless mechanism, and 802.15.4 is what currently is proposed for IoT and CPS deployments, making the range of applications you could build on much, much broader. We then need, as we take away all the networking stuff, an addressing layer that caters to interest or content, and no longer to IP addresses or devices. And on top of that, we make an adoption interface for applications to exploit. So starting from the bottom, the abstraction layer wants to give you, the network abstraction layer aims to give unrestricted access to whatever's in your physical surroundings, wireless physical surroundings. And why do we need an abstraction layer? We don't want to be fixed for one application to one networking service, but we want to be broad in that. We don't want the user of the application to determine which networking technology he wants to use in the first place, but we want to build it. And again, we want to reach network-free communication, meaning you don't have to associate to an 802.11 network, or you don't have to pair with an 802.15.4 network before you can communicate with the guys. But we want to make this broad and spontaneous and open. So we hide the technology characteristics. We give you one layer of uniform sensing and representation. And while we only do 802.11 and 15.4, this is extensible. You could plug in more pillars like Bluetooth Direct. And we cater to the coexistence of 802.11 and 15.4 at the same, because they work in the same media. So we built on this work, which is called CAFI, Concurrent Association with Wi-Fi. In that work, we targeted more mobile ad hoc networking stuff, where you move away from the restrictions of the 802.11 network to go for full exploitation of encounters and location and time-based contacts. And what CAFI does is it minimizes the overhead and the coordination that is imposed by 802.11. So you take away all of the networking stuff out of the wireless frames, out of the 802.11 frames, and simply do transmissions and receptions based on your wireless transmission range. So you hear something or you don't, it's fully opportunistic. And we still, because some applications need the bandwidth and the transmission power, we still support, while we give this full open mechanism, a concurrent 802.11 association that runs simultaneously. So the usage scenario would be device D, which is moving around wherever it wants. It has a full blue circle of its wireless transmission range and can talk to stations that are associated to independent networks. And the stations that are associated to the network can still talk to the wireless device without providing an association. Of course, that needs another mechanism of addressing, because IP addresses and MAC addresses don't work so well in that scenario. So we use the application-specific identifier, meaning you could directly address the wireless frame to, let's say, your social networking handle or identifier. And we try to minimize the overhead this imposes on the wireless medium by aggregating messages and addressing in single frames by using blue filters. So the abstraction layer then builds on that mechanism for 802.11. You get 1 Mbit base rate throughput with 1,500 bytes of payload per frame, and you address this to the layer 2 broadcast address so everyone hears it. And in 802.15.4 we do more or less the same. We employ a broadcast person in the network with the typical 802.15.4 throughput of 350 kilobit per second, but frames are much slower, so much smaller. So that is that's a restriction we can't avoid. We need to cater to the coexistence of these two networking technologies because we employ them at the sender device, meaning they both work with the 2.4 gigahertz ISM band and they interfere with each other when sending at the same device. So we employ a simple temporal slotted sending mechanism where the abstraction layers temporarily slots frames from two technologies. So now we have the open wireless medium to talk to, but we need to address who we want to talk to. So we don't have a network, that means we don't have IP addresses, or at least they would be meaningless. We can address devices based on their MAC address from the wireless frames, but still a device address doesn't give you any information about the content or the application that you can find at that device, so that doesn't work either. And what we propose is a semantic addressing built of 2 tiers. The first tier is directly employed or used in the wireless frame at the abstraction layer, and it gives you a broad category because you want to find stuff based on content, on your interests. So maybe you are into mobile gaming, then you would address your frame to mobile gaming as a category. And that allows you to announce a service and discover services or content based on this category, giving you a rather broad filtering mechanism already on the networking layer. And we can filter that on these interests, these categories, and we can filter that on the location. Although the location is already a bit restricted by your wireless transmission range, you may want to address a specific location. So once we address to a category, that gives you access to let's say, broad identifiers like mobile gaming, but you can't find any specific service in that. So we handle content, we handle applications in terms of one service, and each application is one service, and we need to do that in addressing to send and receive data to that service, and we need to provide a service representation to every application so they can subscribe and interact with that service they discover in the wireless range. And we use this service ID that was already in the previous networking layer frame, which identifies each service uniquely. And that service identifier should provide a specific notion of what that service actually is. So while you have building automation as a category, you would use elevator for floor 2 as the specific service ID, so you can read that and then subscribe to that service if you're on floor 2, or if you want to search for an elevator. Similar, you could distinguish mobile social networking applications by using that in the category social networking, or mobile gaming applications with their own. Of course, that's optional, because if you want to discover stuff, you can't in advance know what's around you, so you can leave that out in the discovery frames, but you can put it in when you subscribe to actual services or talk to a service. Okay, so the last layer we have is the application layer, which provides an interface to applications to make use of that not very standardized interface. So each application may simply register an IP port-faced overlay for adoption purposes. And the primitives are the ones you would expect. You can register and remove a service, communicate with services, and trigger discovery. And all you need is the category your application belongs to and a specific ID or name, but that is rather easy. And you can then control at this application layer what your service does. So you could trigger communication, trigger the behavior of applications based on, for example, the time of the day, or the GPS, are you outdoors, are you indoors, or the sensed wireless context that you can get from the lower layers. So we implemented this on Linux netbooks and Android smartphones. Unfortunately, while everything's possible in Linux, we target smartphones, and smartphones aren't that good to develop with and implement with. So to get access to 802.15.4 in a smartphone, we need to externally attach a radio, and then we do the same for 802.11 to get away from the Broadcom chip in the device and use the Atheros chip on the external device, which is much more, let's say, modular. And we use that to do a technical evaluation first, see if this communication layer without the networking stuff we propose is actually feasible. So I will show the communication performance and the impact of fully uncoordinated communication. The rest is in the paper. And then we build some use cases based on that to show what we actually want to do with it. So let's get started. The communication performance builds on just sending data out without any acknowledgements, without any coordination from something like an access point, and we try this over the various distances, indoors and outdoors, for both wireless technologies. And indoors, you see with 802.11, we get the 100 kilobit per second throughput, and we get high packet delivery rates plotted to PDR. In the upper left plot, in the upper right plot, you see that throughput over distance varies a lot outdoors. That's because of the unstable environment. But we get still around 90 kilobit per second throughput with reasonable PDRs. Indoors with 802.15.4, very stable, everything's fine, we like that product. But when we go outside, everything breaks down quite quickly, which was surprising for us. So this gives you, or gives us already, a sort of functional separation between the two networking technologies, so we can use 802.11 outdoors to get the full range it offers, up to 70 meters with reasonable throughput and delivery rates. And indoors we would use 802.15.4 to simply build upon the locality that 802.15.4 with the limited range proposes and with the stable communication performance. Next thing we wanted to know is if we communicate without all the networking stuff between it, without the coordination, is that actually feasible in terms of when multiple people, multiple senders or context devices want to talk with each other? So we did the worst case analysis. We use 802.11, and on the Mac layer it's still CSMA-CA, robust modulation at 1 Mbit per second, and we just added senders to one interference region. And you see that CSMA-CA and the modulation is quite robust, even if multiple senders are in the same region, but it goes down a bit. But we still get packet delivery rates of 0.4 to 0.8, depending on how aggressive the wireless chipset acts. In 802.15.4, the MAC protocol is similar to CSMA-CA, but we get huge performance degradation as soon as multiple devices send at full throttle. That's what I meant with the worst case. When they send with all they have, performance goes down quite a bit. So that is one indication that we can't just push all the time, which would be very energy inefficient anyway, but we need to announce services, like beaconing in 802.11, and once people subscribe to that service, we give them the database they want to have, but only then. We see that if we just announce everything, with 4 senders and give the payload or transmit all the payload at full throttle once someone requests it, you get very high delivery rates again. So we take that as the communication part is feasible, although the throughput is much less than you would expect from a wireless network with an access point, and still in AR254 it's feasible as well. So we did some use cases based on that to see what can we use with that. And we do, what we want to have is the wireless context based on applications or content within your transmission range. So the natural thing to do would give you this radar-like launchpad where everything is listed in terms of well, persons or entities that provide content. In that view there, we already filtered for building automation as a category and for elevators as a service ID. So there's only the elevator on our floor listed here. You could do other alternatives to visualize the sensed content and applications, but we stuck with the radar launchpad. And that launchpad should then be just the beginning to give you access or to redirect you to the specific application that registered to the service you encountered. So an elevator application would look something else than the launchpad, but would have buttons called elevator or something like that. Visualizing the sensed data could also be application specific once you push that button. And what we liked to do was to build an Ingress-like mobile game that only depends on the locality and only occurs between the participants in the wireless medium. And it looks like that. So I have to say, we built the game, we built the communication part, but we really aren't good at gameplay. So we are also not good at designing figures. This is what you can do. You can attack and you can communicate with people in your wireless range, and you can find landmarks, which is in the screenshots. But we tried to go for the Ingress-like games, and sadly, this is what Ingress looks like. We are not Google or Niantic by far, so we lack the design and so on and so forth. The next use case is the example I brought up in the beginning, in the motivation. What about a walkie-talkie where you just send audio broadcasts to everyone around you? And we did that. We implemented that with the Speaks codec, which I heard is now obsoleted, and we sent audio that you record live with a smartphone microphone in 20 millisecond blocks. It works. To evaluate that, we put 802.11 at 50 meters outdoors and 802.15.04 indoor in an office environment, but line of sight without any walls, in an office scenario where there are walls between the participants. And the main quality metric we want to look at is how bad the audio gets when you are in this uncoordinated wireless communication system. So we look at the maximum audio gap that you can get with our system and compare that against what is tolerable. And that CDF already tells you that most of the gaps occur under the 400 millisecond range, which is nice because the ITU standardizes tolerable faults in audio transmissions between 150 milliseconds and 400 milliseconds. Above that, you would probably click on this call had very low quality when when Skype asks you how the call was. But most of what we do has a gap that is much lower than 400 milliseconds. So you can actually send audio broadcasts that are distinctly. So for the last use case, this is one I really like. If you think of mobile computer vision, if you think of the tasks needed to detect and recognize objects that are in the surroundings, you do need to do two things. You need to take a picture, then you upload it to a central server, to the internet. There it is compared to a database full of similar, hopefully, pictures, and then they can tell you what you are seeing. So the requirement is internet access, the database, and the service that you can upload your data to. And the other requirement is the object needs to be in the camera view because you need to take a picture. And we want to use the second requirement to our advantage, namely, objects that are already in your camera view are rather close to you, and when they hold, and then they should give you the computer vision material that is needed to recognize them in the camera view directly. So what this looks like is you would stand before our office building, and the office building would have an access point that gives you the computer vision material. You are able to recognize the computer vision material in the camera view, and then you could annotate with the information that is given to you by the builder. similar for humans. It works with face recognition as well. So that's one colleague of mine, and you could get the information that he gives you, that he just specifies for that service, along with the computer vision material. So we evaluated that, and we don't have that much space in the wireless frames, so we can't do the typical thousands of descriptors that modern approaches take from the picture. So we use the org descriptor for its low size, and we need to stay below the 802.11 frame payload of 1,500 bytes. That's 40 descriptors. We want to know if this is feasible, and we evaluate the recognition rate based on the number of descriptors we can extract from the feature versus the true positive and true negative rate. So the dark bars are the true positive rate. Do we detect the image with the number of descriptors we have or not? And you see with 80 descriptors we already get up to 80% detection rate, and the true negative rate is always very low. So we never mistake something else for what we are searching actually. It's the same in the face data set provided by someone else. So for a conclusion, I'm over time, sorry, I will hurry up. The wireless application overlay we propose gives you unrestricted access to the multimedia context given by a wireless physical range. The interesting part for us is the interplay between our networking domain and the multimedia domain. So the application requirements actually interfere or cross-fertilize the communication design, so we're very interested in talking to any one of you who has an application that could benefit from that could use that. And with that, thanks for your attention. Any questions?
I guess we have time for 1 or 2 questions.
I'm actually really confused, right? So you basically broke every networking abstraction there is and then some, just so that applications can spend me that code.
Yes, exactly.
Why? There are already ways to do that, including 1,001 service discovery protocols, a lot of PTP.
Exactly, and they all require pre-existing network association.
So they can work unassociated PTP, and that's for 20 years in sensor network. They don't work because nobody wants it.
They don't work because nobody wants it?
Yes, you cannot mention it. You've been working on that for many years as well.
Yeah, that is exactly the point. I would say it's a worthwhile thing to have that in typical everyday scenarios, because there the multimedia context is interesting, is fluctuating and dynamic. In sensor networks, of course, it's a static deployment you have, and you more or less are sure who you are seeing all the time. And pardon me for that, but it works because nobody wants it, and then it doesn't work again. Otherwise,
what I said is nobody uses those techniques because they don't have use cases. There are 20 years of work on P2P, without networks, and the sensor network and it's not deployed because there's use cases.
yes, we definitely need more use cases than the toy examples.
It would be useful to look at that work. That's all I was suggesting.
Yes, I'm very happy to discuss about it.
One last question. Okay, well, thank you. I guess this is the end of this session. We are moving on to the next one.